Microsoft Excel is a valuable tool in science due to its wide range of data handling capabilities. It allows scientists to organize large data sets in structured spreadsheets, making it easy to sort, filter, and label data for analysis and reporting. Its built-in functions and tools help process and analyze experimental or observational data efficiently. In this lecture, you will have the opportunity to learn the basics of Excel and apply them to real-life cases. Let's start with some basic skills in Excel. First, we will learn how to enter data into an empty cell. Step 1 is to click on an empty cell, like cell A1 shown here. Once you've selected the cell, you can type text, for example, a course code like SCI101, or type a number such as 25.1. After typing, simply press Enter to save the entry into the cell. In Excel, if you enter data starting with an alphabetical letter, it will recognize as text, not as a numerical value. Now, let's move on to basic math and statistical operations. Excel can perform addition, subtraction, multiplication, and division easily. In the first example, we want to calculate 2.4 plus 1.7 multiplied by 5. You can select any cell and type the formula directly into a cell, starting with an equal sign like this. When you press Enter, Excel will calculate the result, 20.5, and display it in the cell. Alternatively, if you have values entered in different cells, for example, 2.4 in A1 and 1.7 in A2, you can write a formula that references these cells, A1 plus A2 times 5, and press Enter. This approach is useful because if the values in A1 or A2 change, the result will automatically update. For division, the process is similar. To calculate 2.4 minus 1.7 divided by 5, enter the formula. Excel will evaluate the expression and show the result 0.14. Again, you can reference cell values instead of hard-coding the numbers. If 2.4 and 1.7 are entered in A1 and A2, your formula would look like this, A1 minus A2 divided by 5. And Excel will perform the calculation automatically. Understanding how to enter basic data and perform simple calculations is essential for getting started with Excel. It forms the foundation for everything else we will learn. Now that we know how to perform simple calculations, let's learn how to use Excel to quickly calculate sums, averages, and standard deviations. Here we have a table that tracks Amanda's and John's monthly data from January through June. Our goal is to calculate the total for each person, their average values, and the standard deviation of their data. Let's construct a table in an Excel sheet like the one shown on this slide. Select a group of cells to create a 10 by 3 grid. Position the cursor anywhere within the selected area. Then right-click to open the drop-down menu. Select Format Cells from the menu. Click on the Border tab at the top and choose the desired borderline style. You may also select the border color. Then specify the positions of the borders. Press OK. To shade specific cells, for example, the first row of the table, select the row, right-click on the selected cells, choose Format Cells, and then click the Field tab. Select your desired color. I would choose gray and press OK. I would do the same for the last 3 rows. Enter your data into each cell. Then it will look like this one. We will be entering formulas into the sum, average, and standard deviation rows at the bottom of the table. Here's how we do it. Click on the empty cell where you want the answer to go. For example, under Amanda's sum. Then you can either click the little FX button next to the formula bar. That's where Excel keeps all the built-in functions. Or you can just type a formula directly into the cell. But I will pick the right function from the list of all the built-in functions. Click on Amanda's sum cell. Click on FX, select Sum from the list, and press OK. Click on Amanda's January data and drag down to her June data. Press OK. The sum should display 90. Next, click on Amanda's average cell. Click on FX, select Average from the list, and press OK. Again, click on Amanda's January data and drag down to her June data. Press OK. The average should display 15. Then click on Amanda's standard deviation cell. Click on FX, select standard deviation or STDEV from the list, and press OK. Click on Amanda's January data and drag down to her June data. Press OK. The standard deviation should display 2.828. You can format the results to show a specific number of decimal places. Here, I will format them to 1 decimal place. To do this, select the 3 cells showing the sum, average, and standard deviation. Right-click on the selected cells, choose Format Cells, and then click the Number tab. Select Number from the list on the left, and enter the desired number of decimal places. Press OK. You will do the exact same thing for John's data, but use column D instead of column C. An easier method is to simply copy Amanda's cells containing the sum, average, and standard deviation, and paste them into John's corresponding cells. To do this, select Amanda's 3 cells, right-click on the selection, choose Copy from the drop-down menu, move the cursor to John's corresponding cells, right-click, and select Paste. You will see Amanda's total is 90.0 and John's total is 75.0. Amanda's average is 15.0 and John's average is 12.5. Their standard deviations show how much their numbers are spread out. Amanda's is 2.8 and John's is 6.6. Pretty neat, right? Knowing these quick functions will save you tons of time later, especially when you are working with bigger tables. Alright, now let's talk about one of the most important things to know in Excel: relative versus absolute cell references. First, relative references are the default setting in Excel. When you copy a formula that uses relative references, the cell addresses change automatically based on where you paste it. It's super handy when you are working with lists or tables. Let's do some practice. Open an Excel worksheet and create a 6x4 grid just like the one shown on the slide. Enter the data into each cell. Then it will look like this one. The third column is for the price of each item. So let's add a $sign to the cells. Select the 4 cells containing the prices. Right-click on the selection. Choose Format Cells from the drop-down menu. Click the Number tab at the top. Select Currency from the list on the left, and choose the desired currency symbol. Press OK. The last row is designated for the total price to pay. We should merge the first 3 cells of the last row into one and label it Total. Select the 3 cells, right-click on the selection, and click the Merge in Center icon at the top. You can align the text to the right of the merged cell. Now, in this grocery table, if we want to find the amount by multiplying quantity and price for each item, we can enter the formula for bread like this. Equal C3 times D3. Copy the cell and paste it into the remaining 3 cells below. Excel will automatically adjust the formula to use C4 times D4 for butter, C5 times D5 for cheese, and C6 times D6 for jam. Take note that there is an easier way to do the same thing. Click on the cell and look at the bottom right corner of the cell. You will see a small square. Move the cursor over it until it changes to a thin cross. Then left-click and drag down to the last cell. You can calculate the total expense using the Excel sum function as we did previously. That's relative referencing at work. But sometimes you need one value to stay the same no matter where you copy the formula. That's when we use an absolute reference. You do this by adding a $sign to lock the row, column, or both. $sign A3 locks the column A. $sign 3 locks the row 3. $sign A, $sign 3 locks both the column A and the row 3. Take a look at this ethanol example. We want to calculate the mass by multiplying the volume by a constant density 0.789 grams per milliliter. Since the density is always the same, we need to lock the density cell when writing our formula. Open an Excel worksheet and create a 6x3 grid, just like the one shown on the slide. Enter the data into each cell. Then it will look like this one. Mass can be calculated using the volume and the density of a substance by multiplying the volume by the density. In this practice, we will calculate the masses of 4 ethanol samples using the density of ethanol. Click the cell for the calculated mass of sample A. Enter equal D2 times C4. Press Enter. As mentioned previously, relative references are the default setting in Excel. So, if you simply copy the cell and paste it into the remaining 3 cells below, the results will not be as expected. This is because the density cell is not locked for those calculations. To fix this, lock the density cell D2 by adding a $sign in front of both the column letter and row number like this. Equal $sign D, $sign 2 times C4. Press Enter. The result for sample A will remain the same, but now the formula will always refer to the exact same density value. Copy the cell and paste it into the remaining 3 cells below, and Excel will produce the correct results for all samples. So here's a summary. Relative references move with your formula. Absolute references stay fixed and always point to the same spot. Knowing when to use each one will save you tons of headaches. when building more complicated spreadsheets. On this slide, you can see a clear example of how we take raw data, plot it in Excel, and extract important parameters like the slope and y-intercept from a linear relationship. On the left-hand side, we have our experimental data. The first column shows time in seconds, and the second column shows distance in miles traveled by our vehicle. Our measurements start at time 0 with a distance of 0, and they go all the way up to 112 seconds, where the distance covered is 1.81 miles. Take note that the distance traveled by the vehicle increases linearly as time progresses. In this practice, we will plot the data in an Excel worksheet, determine the equation for the trend line of the plotted data, and use this equation to predict the distance traveled after a given driving time, even if that time falls outside the range presented in the table. Open an Excel worksheet and create a 10 by 2 grid, just like the one shown on the slide. Enter the data into each cell, then it will look like this one. Select the entire table, click on the Insert tab at the top, navigate to the Charts group, and click on the Plotting option called Scatter. Select the first option, Scatter. On the right-hand side, you can see the resulting chart. The horizontal axis represents time, and the vertical axis represents distance. Make sure there are no lines connecting the data points. Move the cursor over one of the data points and right-click on it. This will bring up a drop-down menu. Select Add Trend Line. A dotted trend line will appear on the plot. The trend line represents the best fit straight line through our data points. On the right-hand side, you will see the Format Trend Line panel. At the bottom, check Display Equation on Chart and display R-squared value on chart. The R-squared value should be higher than 0.980 to ensure an acceptable degree of agreement between the trend line and the plotted data. Now, we will add axis titles. Click on the plot, and you will find two new tabs at the top, Chart Design and Format. Click on the Chart Design. Navigate to the far left and click Add Chart Element. From the drop-down menu, click Axis Titles and select Primary Horizontal. Type the title Time in Seconds. Go back to Axis Titles. Select Primary Vertical. Type the title Distance in Miles. Excel can display the equation for the trend line directly on the chart like the one we just created. Y equals 0.0156x plus 0.0312. Y is the distance in miles. X is the time in seconds. 0.0156 is the slope of the line, and 0.0312 is the y-intercept. So, what does this mean in real-world terms? The slope of 0.0156 means that for each second that passes, the vehicle travels about 0.0156 miles, or roughly 82 feet per second. In other words, the slope in this case is the speed of the vehicle. The y-intercept of 0.0312 means that if we extrapolate back to time 0, our model predicts a small starting distance offset, possibly due to the measurement error or the fact that the vehicle was already moving when we started timing. This equation can be rewritten as distance equals 0.0156 times time plus 0.0312. The equation can be also modified with respect to time like this. Here are a couple of practical questions that we may encounter in our daily lives. How long does it take for the car to travel 2.76 miles? In order to find the answer, we should use our time formula. Plug 2.6 miles into it, and it gives us 174.9 seconds, or 2 minutes 54.9 seconds. Pretty neat, isn't it? Our second question is, what is the distance the car travels after 5 minutes or 300 seconds? To answer the question, we should use the original equation. Plug 300 seconds into the equation and it gives us 4.71 miles. This process, starting from raw data, creating a plot, finding the slope and y-intercept, forms the foundation for analyzing linear relationships in experimental data. It not only helps visualize trends, but also allows us to extract meaningful physical parameters, such as speed in this example.